Welcome back, everybody. Today we're going to talk about how to use a normal approximation for a binomial distribution. Sometimes we use this. We use a normal approximation to estimate a binomial distribution. Most importantly, to make the problem we're trying to solve easier. However, it's currently very often used in statistical inference for proportion, which we will get into later in these videos. So when we were talking about the binomial distribution, let me grab blue, there we go. When P, which was our probability of success, was 0.5, we found that the binomial distribution was symmetrical. All right, well, symmetrical definitely means that we could use a normal. However, P doesn't always have to be 0.5. It can be other things, especially when n is large. Are we going to get closer and closer and closer to approximating a normal distribution? So the test we have, the test to check if we do have a problem where we could use the normal distribution as a good estimate is that if n times p is greater than or equal to 5, or n times q, or not or, excuse me, and is greater than or equal to 5. All right, so if both of those are true, we could use the techniques we've just learned to solve a normal distribution to solve these binomial type problems. And again, it is an approximation, but it's a good approximation and it makes the problems much, much easier. All right, still just as a reminder, our mu is still going to be n times p, and our variance is going to be n times p times q. And as always, z equals x minus mu over our standard deviation. All right, so here's our first example. Now there's no context. I've just stripped it down to the math so we can start working on this new technique. So let x be a binomial random variable with n equaling 75 and p equals 0.6. What is the probability that x is greater than or equal to 52? Now, when we did this as a binomial, right, I started by saying greater than or equal to 52 equals 1 minus the probability that x was less than 51, right? And then to get the probability that x was less than 51, I needed the probability of 0 plus the probability of 1, all the way up to 51. And I don't know if you want to do that. I certainly don't. It's going to take an awfully long time. Those people that need to do this to get an exact answer very often will use a computer to do this. So we're going to use, if we can, a normal approximation. So the first thing we need to do is check. We need to check the test to see if we can use our normal approximation. So our mu equals n times p, which equals 75 times 0.6, which equals 45. N times q equals 75 times 0.4, which equals 30. Both are above 5. which means we can use our normal distribution. So in order to get z, I need my mu, right? So now we're going to find z. In order to find z, right, I'm going to use z equals x minus mu over our standard deviation. I'm going to make that a better z just because I want to. All right, and our mu we already calculated was 45. Our variance is going to be 75 times 0.6 times 0.4, which equals 18. So our standard deviation equals the square root of 18. All right. And you can convert that to a decimal. I definitely would endorse not rounding as long as possible. All right. So next thing I want to do is I want to take a look at my graph. So, or actually, you know what? We said we're going to find z, so let's find z. What the heck? All right, so z equals our x, which is 52 minus 45 over the square root of 18, which equals 1.645. All right, that's kind of a special one. It's so we'll see what it looks like in just a second. But if I were to draw a graph just to see what I'm looking for, there's 0, there's 1.645, and I'm looking for that area over here. All right. All right, and if we were to, hang on one second. Draw out the graph. There's 0, there's 1.645. And we looked that up on the chart, because that's the area we're looking for. We find that it's right in the middle of two values, 1.64 and 1.65. And the area behind it would be 0.95. The area in front would be 0.05. So that would be our answer. All right. Now, if we did this with a regular binomial, right? So distribution. Our answer would be 0.0611. So we can see there's a little bit off. All right. Now, are there ways we can improve this? Absolutely. All right. We can improve it with something called our continuity correction. All right. And basically what our continuity correction does is, do you remember when we started talking about continuous random variables and I said it's really hard to land on exactly 10 minutes. Like you say, I can read a chapter of a book in 10 minutes, right? What you're really saying is you can read the chapter of the book in about 10 minutes, meaning somewhere between, let's say, 9 minutes and 50 seconds and 10 minutes and 10 seconds. Kind of, there's a little bit of a continuum there, right? It was very, very difficult to take a continuous random variable and say, I can stop at exactly 10. And likewise here, even though the binomial is a discrete variable, we're trying to convert to a continuous normal variable. So to say I can do exactly 52, very, very difficult in the discrete sense. So if we're talking about 52, we're really saying that I can do somewhere like 51.5 less than or equal to x less than or equal to 52.5. I'm not saying exactly 52. I'm saying somewhere in that very, very small range. Okay? So if I'm looking for the probability that, what is our probability again? That x was greater than or equal to 52, right? What I really want to say is it's approximately equal to the probability that x greater than or equal to 51.5. So I capture that little extra either behind or above. And now I'm going to redo my z-score. So I'm going to redo my z-score with 51.5 and say 51.5 minus 45 all over the square root of 18. All right, and when I do that calculation, I get 1.53 rounded to 2 decimal places. So from there, I go to my chart, I do my area, and I find that my area is 0.63, which is, as we can see, much, much closer to our binomial distribution. All right, so the next situation I want to put you in is, what if we wanted our probability that x was greater than 52? All right, so just so I guarantee that I don't get any part of 52 in there, I have to do my continuity correction to say I'm going to approximate my probability that x is greater than 52.5. I already checked to see if I can use the binomial, so I don't need to check again because I'm using all the same numbers. So my z-score equals 52.5 minus 45 all over the square root of 18. And when I do the calculation, I get 1.77. All right, so now I want you to pause the video and on your own, go to your chart, get your area, do the rest, and we'll see what the answer is on the back end. All right, so I'm hoping you found the right area, did 1 minus that area, and I got an answer. Excuse me, that does not say answer. Answer of 0.0384 as my area. All right. The next situation is, what if I wanted to know the probability that x was less than or equal to 52? All right, because I have the or equal to, we need to do the probability that x is less than or equal to 52.5, just to make sure that I get that little extra on either side of 52. So when I do my z-score, right, it's going to be the same calculation. So I get z equals 1.768. All right. However, if I'm looking for the area less, once I find the area on my chart, I'm all done. So the area on the chart is 0.9615, and that is my indeed answer. All right, the last situation that I want to put you in is what if I wanted the probability that x was just less than 52? Well, then I need to make sure that I don't get any of that little 52 in there. So I don't get the, right? I don't get the 52, don't get the 52.5. I actually want to say my probability that x is less than 51.5 would be my continuity correction. So I want you to pause the video, do your z, and we'll see what it is on the back end. All right, I calculated z to equal 1.532. So we're going to say 1.53. And because we're doing area less, I want you to go to your chart, look up your area, and that is your answer. So go ahead and do that now. All right, hopefully you did that. And I got an area of 0.9370, if I read it correctly. All right, so just a summary of the continuity corrections when I was doing the probability that x was greater than or equal to 52. I used, right, probability that x, right, was greater than or equal to 51.5 if the probability of x was greater than 52. I used 52.5. Z is greater than. So I'm going to do that instead. So let's alter that to say, not really changing anything, I'm just going to write it better. All right. So then if I wanted the probability that x was less than or equal to 52, I use the probability that z was less than 52.5 minus mu all over our standard deviation. And lastly, probability that x was less than 52. I use probability that z less than minus, and let me scroll up a little bit, minus mu over our standard deviation. So this was kind of a summary of all the things we just did. Now, I wouldn't be me unless I added at least one problem with a little context to it. So here it is. 38% of people in the US admit that they snoop in other people's medicine cabinets. You randomly select 200 people in the United States and ask if he or she snoops in other people's medicine cabinets. What's the probability that at least 20 will say yes? Now, this is fairly apparent that it is a binomial distribution. But if we're talking about a group of 200 people and you want to find the probability of at least 20, that means probability of 20, probability of 21, 22, 23, 24, 25, all the way to 200. We certainly want no part of, and the keywords are right here, at least 20. All right, so first thing I want to do is I want to check to see if I can use my normal approximation. My n times p equals 200 times 0.38, which is our probability of success. That equals 76. My NQ is 200 times 0.62, which equals 124. You're welcome to check my work. But it looks like we can use the normal approximation because both of them are greater than or equal to 5. That is good for us. So the next thing we need to do is we need to find mu and our standard deviation, and then our z-score, which equals x minus mu over our standard deviation. So why don't you pause the video, work on each one of these, and we will talk about it on the back end. All right, so hopefully notice that we already found mu, because our mu equals n times p, which we found up here to be 76. And our standard deviation is the square root of n times p. That's a terrible looking start for a q. Q, which I got to equal about 6.86. And so now we can fill in the rest of our z formula with our continuity correction. So let's look back at the problem. So we are looking for all right, so look back at the problem. I wanted to use the number 70 instead of 20. So I took the liberty of changing it. So please change it on your paper. My apologies. But the numbers for me come out a little bit better. So if I'm going to use my continuity correction, I want to know the probability that x is greater than or equal to 69.5. All right, so my z is going to equal 69.5, right, minus our mu, which is 76, all over our standard deviation, 6.86, and I get negative 0.95. So now go to the chart, get your area, do 1 minus that area, and we'll talk about it on the back end. All right, so when you go to your chart, I do believe that I got an area of 0.1711. I do 1 minus that, and I get an area of 0.8289. All right, so my final sentence will say, so the probability that 70 will say yes, is 0.8289. And there you go. All right, so that ends our mini lesson on the normal approximation to the binomial distribution. Hope you enjoyed what I had to say, and I look forward to seeing you guys soon. Thank you.